We'll solve roughly maybe 5 to 6 problems. Most of them are related to flash distillation, and there are some slightly tougher questions that are related to distillation columns. So we will see one by one. So let's begin with the easiest problem. So the first one is draw a flash column. So this is a purely theoretical question. It's not even a mathematical, or there is no mathematics involved. Yeah? So all you're going to do is some derivation. So what I asked is draw a flash column and derive the mass balance equation. So you need to perform some mass balance in order to calculate the mole fraction of the volatile component, so which is going to be y in the vapor phase, expressed as a function of, so y should be expressed as a function of fractional vaporization and the concentration of the more volatile component in the feed, which is xf. So other question is explain how the y and x will be obtained using the txy diagram. So problem is very simple. So this is something I already solved during week 2 as part of tutorial 2, but nevertheless we can do it one more time. So begin with f xf. So it is, if you remember from the lecture 2, how the flash column setup will looks like. It starts with heating your feed, followed by a valve to decrease the pressure. So so increasing temperature should increase the partial vaporization, and decreasing the pressure should also partially vaporize the feed liquid. So, and then you pass the resulting two-phase mixture into a flash drum. Let's call the top product as V and the bottom product as L, and the mole fraction of the more volatile component in the vapor as Y, and the mole fraction of the more volatile component in the liquid as X. So all I ask you to derive is to derive some function which looks like this: Y is equal to function of fractional vaporization F, comma XF. XF is something related to the mole fraction of the more volatile component in the feed, which is here. Yep. So how to do that? So perform the overall mass balance. So F is equal to V plus L, that should be equation 1, and then do the component balance for the more volatile component, Vy plus L into X. So you divide both, so we have to derive something as a function of Y. So let's write Y is equal to Fxf minus Lx divided by F divided by F, and let's replace L with F minus V. So this comes from equation 1. So this equation becomes Y is equal to, so FF get cancelled, so let's write it no, this is not correct. So Y, so this should be F divided by V, and this should be F divided by V. So let's rewrite it, sorry. So by V, so because we have Vy, so Y should goes to the denominator. So how to write this? Let's rewrite it. So Y is equal to Fxf divided by V minus L, we can replace it with minus F minus V by V into X. So we already have some function which is Y is equal to a function of F, V, Xf and X, something like that. So what we need to do, so we have to express this whole function in the form of fractional vaporization. So let's define fractional vaporization as V by F. So what's this? If F is equal to 1 and if V is equal to 1, which means 100% of your feed is vaporized, then F will become 1. If it's 50% of your feed is vaporized, then V will be equal to 0.5, F will be equal to 1. Then fractional vaporization will be equal to 0.5, so which means 50% of your feed mass is vaporized. So that's how we define the fractional vaporization. So plug in this equation into here. So y will be equal to x of by small f, which is fractional vaporization, minus, multiply and divide both the numerator by f for convenience. So let's do that. F by f minus v by f divided by v by f, so multiplied by x. So what is this? So if f get cancelled, v by f is nothing but fractional vaporization, v by f is nothing but fractional vaporization. So this makes so thus we can transpose this equation into some simple form. X of by f minus 1 minus f by f into x. So something we derived, y as a function of x, and fractional vaporization. So this solved the first part of the question. So we already answered something. So this is what we asked, and then the second question is I also ask you to explain how do you get x and y from the txy diagram. So typically your txy diagram will look something like that. So t will be on the y axis, x comma y will be on the x axis, so something like that. So the topmost curve is t versus y. So if you want to, so if you know the feed, the mole fraction of the feed, the mole fraction of the more volatile component in the feed, then we can determine the temperature at which that particular fluid will boil. If say x of is equal to 0.5, so this fluid will boil at T1. So if x of is equal to 0.5, then the liquid boil at T1 degrees centigrade. And then I also ask you to tell how to determine the x and y after after the flash vaporization. So how to do that? So you have to draw some image. So how do you do that? So say if the partial vaporization is, or if the fractional vaporization is equal to, so let's say if the fractional vaporization is equal to 10, for example, or maybe 50, then you know how to get the corresponding x and y. Sorry, fractional vaporization is equal to 0.5, which is a 50% vaporization. Then from the txy diagram we can easily calculate the x and y. So if we go up again, so we know that y is equal to x. So we know that y is equal to x of by f minus 1 minus f by f into x. So to get x and y as a function of vaporization, so from the xy diagram, locate x of comma x of. This is something we already proved in the tutorial 2. So this equation should pass through the point xf comma xf. If you don't know how, watch tutorial 2. xf comma xf, and then it should also pass through x comma y. So if you want, I can prove it one more time. So if x is equal to x of, y is equal to x of by f minus 1 minus f by f into x of. So if you expand, this will become x of by f minus x of by f plus x of into f by f. So this get cancelled, ff get cancelled, so become x of. So this means this equation, which looks like a straight line with a slope m is equal to minus 1 minus f by f. So there is something. So if we take a xy diagram, diagonal line is here. So this is 1 1 0 y x. So, and we know that this line passes through the point x of comma x of. Say if x of is 0.5, so x of comma x of, that point should lie on the diagonal line. So this should be 0.5 comma 0.5, and this should line have a slope that should be equal to minus 1 minus f by f, and then that slope should also cut at x comma y. So when x is equal to x, it will cut y is equal to the whole function which is given by this one. Yeah? So when x is equal to x, y will be equal to y given by this whole equation. So that's what the equation states. So which means that x comma y should lie somewhere on the vapor liquid equilibrium data, which is here. So follow the red color. So that x comma y point should lie somewhere on the xy line. So it should be somewhere here. So wherever the straight line equation cuts in the vapor liquid equilibrium curve, so from the point where the equation of straight line, let's call this equation A, as in equation A cuts the VLE data or XY data, draw so wherever it cuts the corresponding X Y corresponding X and Y should be equal to the expected concentration of the more volatile component in the liquid and vapor phase respectively. Yeah. So once we know the x and y, this is something you have to write like this in the exam. So once we know the x and y, then from the txy diagram, we can identify the temperature in the flash drum. Say if x is equal to, so let's draw some line here. Say say x is equal to 0.4, say y is equal to 0.6. Say if x is equal to 0.4 and y is equal to 0.6, or y is equal to 0.6. Yep. So we can determine the temperature in the drum. So go back to txy diagram. From the txy diagram, say if x is equal to 0.4, that is somewhere around here, the corresponding temperature in the flash drum, so let's say T2, and let's say x equal to 0.4. So you have to explain clearly